And good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series, dedicated to you, the research and academic quantum communities. Now, in just a minute, I'll be thrilled to roll out this week's episode with our very own from IBM Quantum, Andrew Eddins and Youngseok Kim, who join us here on stage. As is our tradition, before we get there, I'm so glad you joined us on time because we like to give everybody about a minute or two to tune into the live stream and answer our favorite question, which is, where are you guys tuning in from today? You can reply to that in the comment chat box here on YouTube, located somewhere on your screen, above, below, left or right. That's the same place where you can ask questions live of Andrew and Youngseok as we go through this seminar. And I'll try to bring those questions up to Andrew and Youngseok. And we like to keep it lively, have a discussion both between you and our speakers, as well as oftentimes there's discussion that just comes up between you guys as well. And I see that today we have folks from New York City, from Boston, Mexico, Colombia, Portland, Oregon, Santa Barbara. Hello, Kelly. Great to see you again. Italy, Spain, India, Netherlands, Texas, and I see more names streaming in. So thank you, everybody, for making all the different time zones. Oh, YKT, Yorktown, my former hometown. So folks, this seminar takes place every Friday at noon Eastern Time. We will have a recording that stays up, but you can only ask questions live during the seminar. To know what's coming up, click like and subscribe. And I think with that, it's time we introduce our very special seminar today on this recent Nature paper from IBM Quantum, which has certainly generated a lot of very interesting discussion in the community. I'm very excited to briefly introduce here our not one but two speakers, Andrew and Youngseok, who will join us for the 130th episode of this seminar. Hello, Andrew. Hello, Youngseok. How are you guys today?
Hi, Zlatko. I'm doing good. Thank you.
Good. And where's each of you tuning in from?
Andrew, you're muted.
And we'll give Andrew a minute here, since Andrew will be our first speaker.
Yeah, I'm tuning in New Jersey.
New Jersey. And Andrew, I think we got you unmuted now.
All right. Hey, everyone. I'm tuning in from the IBM office in Cambridge, Massachusetts.
All right. So, folks, according to our tradition, allow me to introduce Andrew and Youngseok briefly before I hand over the stage. Youngseok received his bachelor degree in EE from Postdoc South Korea, his master's and PhD degrees in EECS, electrical and engineering and computer science, and computer engineering, from the University of Illinois, Urbana-Champaign. Youngseok is now an RSM, or research staff member at IBM TJ Watson Research Center, my home base. And Andrew received his bachelor from Amherst College and his PhD from UC Berkeley with Irfan Siddiqui. Fun fact, same group as my bachelor group. And Andrew is an IBM research staff member in Cambridge, Massachusetts. So Andrew, I think with that, the stage is yours.
Great. Thank you, Zlatko, and thank you, everyone, for the opportunity to speak here. Today we'll discuss the results from our paper titled Evidence for the Utility of Quantum Computing Before Fault Tolerance. And this is really a paper about, what can we hope to do with a noisy quantum computer in the near term. So I'll be presenting the first half, and then Youngseok will take over for discussing more of the experimental results. Beyond Youngseok and I, a lot of people contributed to this. This is very much a team effort. So I'd like to acknowledge these folks in IBM, our collaborators at UC Berkeley and Professor Zalatel's group, and also the broader IBM quantum team. And to make that broader acknowledgement a little more explicit, I wanted to just flash up the broader IBM quantum team. That's a little challenging to put on a slide, but wanted to recognize the large effort from many people. So just to start with an excerpt from the abstract, here we're reporting experiments on a noisy 127 qubit processor and demonstrating the measurement of accurate expectation values for circuit volumes at a scale beyond brute force classical computation. So we argue that this represents evidence for the utility of quantum computing in a pre-fault tolerant era. So in other words, The main takeaway that we're hoping to convey is that quantum computers today can provide reliable results at a scale that's beyond exact brute force classical computation. This is not a quantum advantage claim, but it does motivate trying to obtain value from using error mitigation to compute, to estimate expectation values, even in the era before fault tolerance. So this may be a surprising notion that we can get value out of a noisy quantum computer, or do something with a quantum computer that might be hard for a classical computer. Certainly looks that way if you think about the error rates on the hardware, on the respective hardware for these devices. The error rate on a quantum computer, even a good quantum computer, is something like an Avogadro's number higher than the error rates on a classical transistor. The usual conventional wisdom on this is that we'll need quantum error correction to overcome this. We'll encode quantum information in some larger network of qubits to protect that information from errors, especially local errors that happen on the device. And long term, that still seems to be the case, that we need error correction to access the full potential of quantum computing, run things like Shor's algorithm, and so on. In the near term reality, though, is that the expected error correction overhead for conventional error correction schemes seems to be prohibitive, or at least very limiting, as we'll need very large numbers of qubits to realize physical qubits to realize one logical qubit. There has been significant progress in improving the quality of devices. So this is a distribution of 2-qubit gate errors across a few generations of Falcon devices. We see this generation generally moving left, and here lower is better. And also improvements in terms of quantity of devices. So going from IBM Falcon with 27 qubits to Hummingbird 65 qubits, and Eagle with 127 qubits. And perhaps remarkably, it's just with this increase in scale, we've also managed to maintain this increase in quality of the gate performance. And very recently, there's also been brought online the Osprey device with 433 qubits. So this is encouraging trends. But if we think about just a simple back of the envelope calculation, for like thinking about the fidelity of actually running a large circuit, and say we're targeting something with 100 qubits and 100 layers of 2-qubit entangling gates, so 100 gate depth. This gives us in the ballpark of 10,000 2-qubit gates, modulo factors of 2. And then even if our 2-qubit gate fidelity is on the order of 3 nines, the estimated state fidelity at the end of that circuit is going to be something like 10 to the minus 4, when that number ideally should be 1. So that's a discouraging prediction, but we can maybe ask if there might be a loophole in that this number is describing how well the full quantum state has been preserved, as we might think about for quantum error correction. But could it be that that's a more difficult task than just estimating properties of the quantum state of interest? And it's just a simple cartoon to motivate this possibility. We can imagine there's some state that we're interested in for a spin system. Suppose this state is fully magnetized, so all the spins are pointing up, and the true value of interest is a magnetization of 1. That's what we'd like to be able to learn. We try to prepare this state on a noisy quantum computer. An error happens. In this minimal example, we'll say it just flips a single bit. The fidelity of this case, of this state with respect to the target state now is 0, because the 2 states are orthogonal. But the magnetization is largely unchanged. It's still 0.998, and that may be a perfectly acceptable estimate of the property of interest. So again, this is a simple example, but it at least illustrates that there might be some separation between fidelities and the ability to get out useful results. So our expectation values, something that we're interested in measuring. We think so. You can look at properties of spin systems like magnetization or correlation functions. You can look at machine learning kernels, optimization cost functions, molecular energies, and chemical simulations. And generally, measuring expectation values from these shallow quantum circuits seems to be a core primitive of most near-term algorithms that have been proposed. So the way that we'd access this information accurately on a noisy quantum computer is through quantum error mitigation. So just to briefly introduce the idea, whereas error correction, we'd be trying to detect individual errors as they occur during an experiment and essentially use that information to repair the quantum wave function in real time. And error mitigation will instead be learning the distribution of errors that happen on the hardware, so essentially a noise model, as we'll call it through the rest of the talk, and use that information to instead repair the classical average results in post-processing. So this can be an easier task, though it does come at typically an exponential computational cost. So these ideas were introduced in some of these earlier papers, and you can check out the references for more information generally. One example of quantum error mitigation that we'll focus on is zero noise extrapolation, or ZNE. It's a relatively straightforward idea in that we will run the experiment try to estimate some expectation value of interest. That result may be biased from the true value due to noise and errors in the hardware. But if we can somehow, and we'll discuss the implementation later, somehow amplify this noise uniformly across the device, we can repeat the experiment in that noise amplified condition, get a result that's worse, but then look at the trend and estimate what would the result be if the noise were removed or turned down. And this rather simple idea has proven to be proven to be quite fruitful across a range of experiments. For example, this simulation of lithium hydride, the red dots were the original unmitigated results. So corresponding to this point in this cartoon, the noise amplified points are a little bit further from the results, or we're, again, not worrying about the method, but we're essentially amplifying the effect of the noise on the hardware. And then the extrapolated points are the solid green, which are much closer to the correct result for this model of this molecule. So that, since this slide is now looking at scaling up this technique to larger experiments. So on the vertical axis, the two axes represent the size of the experiment, of the quantum circuit that's been run. On the vertical axis is the number of qubits, horizontal, the number of layers of 2-qubit gates, or the depth of the circuit. In the lower left, we have the experiment from the previous slide, several additional experiments using another technique known as probabilistic error cancellation. And then also this, somewhat recently, this result using zero noise extrapolation on a Falcon chip using 26 qubits and a gate depth of 120 layers of CNOTs, and that was still able to estimate expectation values correctly at the end of this long circuit. So in this latest paper we're discussing today, we're using all 127 qubits on an Eagle processor, running circuits with a gate depth of 60, and are able to get out accurate results as we'll discuss. So having crossed these two 100 thresholds individually, it gives us some confidence in our next goals of targeting circuits on the order of 100 by 100 or greater. So what made this latest experiment possible? Well, first was just building a system with 127 qubits, building these chips and growing the processor size is a major in the hardware and software stacks. Key aspect of this is coherence improvements. So even among different generations of the same 127 qubit sort of model of processor, an earlier generation, Washington, had a median T1 of about 100 microseconds, while the device used for this experiment, Kiev, had a median T1 in the ballpark of 250 microseconds. So that gives us significantly more breathing room to run the experiment. Also, the advances in device calibration allow us to improve the performance of our gates. So for example, if we are calibrating the device we used to calibrate each of the gates sort of individually. So that's something of a local optimization of the performance of the gates. As we were developing this experiment, it became clear that if we know in advance which gates are going to be run simultaneously, such as all the red gates here, we can use that information in our calibration, calibrate that entire layer of gates, and get some boost in performance that way by doing more of a global optimization. So here's one plot indicating some of the improvements, the result of that, and other improvements that boosted reduced the median gate error below 1%. And finally, improvements in noise modeling and error mitigation have been helpful. And this includes both scalable characterization methods for learning the noise on the device, and also more accurate methods for more accurately amplifying the noise for the zero noise extrapolation procedure. So I'll spend a few slides discussing these.
Maybe Andrew, quick question before you dive into the PEC slides. Roughly, how much of an improvement did you roughly see with this context-aware calibration?
I might have to defer to Youngseok on that, as he is more of an expert in that particular detail.
Yeah, if I chime in, so one of the biggest benefit we can get from this context-aware calibration is that previously we didn't really know whether there is some additional error coming from running these two qubit gates simultaneously. For instance, there is some spectator-related error or some multi-phonon process involved, inducing somewhat significant amount of leakage, for instance. Those didn't really captured in previous individual approach, but in this context-aware calibration scheme, it is possible to catch that, and we can factor that into calibration scheme.
Great.
So we often see some of the outliers, particularly bad when we run everything simultaneously, but we can capture that kinds of errors.
Okay. Here. So it's like a 5-10% improvement, say ballpark.
Yeah, probably.
Okay, no worries. Okay, thank you. We press forward.
All right, thanks. Right, so going into learning about the noise, we'll think about how we want to construct our noise model, and first we'll think about how we want to model the noisy circuit we're trying to run. So we'll make a series of simplifying assumptions where try to be judicious about this. So first thing is that typically the two qubit gates are the dominant noise source. The 1 qubit gates are generally much higher fidelity. So we'll neglect the small amount of noise that's happening in the single qubit gates and just model the 2 qubit gates as containing the noise. To do this, we'll represent the actual 2 qubit gate that's run in terms of an ideal version of that gate, and a noise channel that contains all of the effects of decoherence, control errors, crosstalk, and so on, generally things going wrong. Now, a general many-qubit noise channel has an enormous number of parameters that one could learn. It's very general. There are a lot of different things that could go wrong. So another simplification that we can do, this is a representation of it in terms of an object known as a polytransfer matrix. Many parameters are not shown here. But a simplification we can do is to use PolyTwirling. So that's discussed in some of these references. And we'll introduce, each time that we run the circuit, we'll introduce a series of random single qubit poly gates rotations just before each 2 qubit layer. And then we'll follow the layer with the appropriate polys such that the 2 layers of polys cancel one another. So in the case of an ideal, in the case of an ideal circuit, or excuse me, these 2 layers of polys thus have no effect on the behavior of the ideal circuit, but they do have an effect on the average behavior of the noise. For example, sometimes a qubit will go through this layer of polys and it'll be pointing up, and other times it'll be flipped here by an X poly and be pointing down. And this 50-50 probability leads to, and there are other polys, of course, but these 50-50 probabilities lead to, on average, many terms in the noise canceling, such that only on average, the diagonal terms in the Pauli transfer matrix survive. So that's first big simplification, but there's still an exponential number of terms to learn in the noise. So we'll make a further simplifying assumption, which is that errors are generated locally. So we'll say that the Pauli channels that comprise our twirled noise layer are either weight 1 or weight 2. So errors are generated either on individual qubits or on nearest neighbor pairs of qubits. And so now this is now a polynomial number of terms in this model, since these effects are happening locally on the device. We can also learn them in parallel, since these are localized processes. And so the experiment and number of parameters is tractable now. The number of parameters is polynomial in the size of the circuit. You could imagine if you were able to just run the noise channel in isolation, you might learn these diagonal terms in this Pauli transfer matrix by preparing a particular Pauli basis state, applying some number of copies, d copies of the noise channel, and then measuring in that basis to see how much that expectation value has decayed. It would decay by the particular relevant Pauli fidelity raised to the number of times you applied the layer. Reality is slightly more complicated because we can only run the entire noisy 2-qubit layer. So there are these extra gates in addition to the noise channels. This leads to needing to make another assumption to address this, and details are in these papers. So we'll need to run experiments to test whether this is working in practice. But with another assumption of symmetry, is essentially assumption about the noise model, we can back out the error rates of all the particular local error sources that are happening inside of our noise channel here.
There was some questions in the audience about the learning model, but maybe I can also help out and add. There's a Qiskit seminar that goes into the whole kind of probabilistic error cancellation here. I'll try to post the link in the channel. That one's from me, I guess. But if you guys are interested in more details on this, that's another kind of more pedagogic place to look.
Thanks. Yeah, if we have time at the end, I'm also happy to take questions. From doing these fitting and looking at these decay curves of the different Pauli expectations, and I maybe omitted one other detail I'll just add, is that we only need to look at the decays of weight 1 and weight 2 Paulis. That's sufficient information to get out this information. So that keeps things tractable. So we can then extract our noise model. So this is comprised of the rates at which the different single qubit or 2-qubit Pauli errors are generated. Those are encoded in the color code on this map of the device. The 3 sectors correspond to the X, Y, and Z rates on each error rates on each qubit, and the 9 small inset rectangles are the rates for the 2-qubit Paulis. So we've reduced the model complexity from this exponential 4 to the 127 down to only 1,700 parameters. And these can, again, be learned in parallel across the device. So with this noise model in hand, we'd like to perform zero noise extrapolation, and specifically, we'd like to amplify the noise. Suppose this is our circuit that we'd like to run. We have some single qubit gates, and then our noisy layer of 2-qubit gates accompanied by the noise channel that is representing the hardware noise happening on the device. So if we think about what this is doing, since it's a Pauli channel, we can think its effect is equivalent to if every time we ran the circuit, this introduced a random Pauli error sampled from that distribution, from that noise model that we learned in the previous slides. So since we know how that, since we now have that noise model in hand, there's nothing stopping us from introducing our own version of this by sampling from the same noise model and applying random Pauli errors accordingly. If we do this, the math works out with these 2 channels combine to effectively double the the rates at which errors are generated if we're sampling from the same distribution. So this would give us a noise gain of 2. There's, of course, nothing stopping us from varying these probabilities continuously, so we can turn that knob up and down to to amplify the hardware noise across the device by any factor that we choose, any noise gain factor, which will represent sometimes as G. And so just as a quick example of what this looks like, this is plotting an expectation value measured on the circuit. I'm not too worried about what exactly we're measuring just yet, but the ideal value in this example would be +1. When we run on the hardware with a noise gain of 1, so not introducing these extra errors, we accumulate more data, and it averages converging towards near 0.8, so somewhat removed from the correct, or somewhat biased downwards from the correct value. We can rerun the circuit, introducing errors at a rate of something like 0.2, such that the net gain, including the intrinsic hardware noise, is 1.2. This is now biased further from the true result. And again, at 1.6, again, accumulating these randomized instances, resampling polys each time, and converging to a further value. We can plot these as a function of the noise gain and fit them with a simple model, either a line in light blue or an exponential in dark blue, the latter being motivated by some theoretical studies in the literature, and find that and then use that to extrapolate back to the zero noise condition and find that the bias is largely removed. This is a particularly nice example, but we do see that this seems to be working well across the range of experiments we've investigated so far. And speaking of experiments, I will now pass it over to Youngseok to talk more about the results.
Okay.
Unless there are questions or anything before that. But if not, feel free to take it away, Youngseok.
Yeah, thank you, Andrew.
Go ahead. Maybe a quick question from the audience was on the relationship between this and PEC, the probabilistic error cancellation method. I think there was a little bit of discussion about that. Maybe if you want to elaborate.
Yeah. First, to try to control the scope, I didn't really get into PEC, but it's definitely a related method. There we're sampling essentially from a quasi-probability distribution. So we are sampling from a distribution such that between the polys that we introduce and also the post-processing that we do, where we introduce minus signs, we're effectively have the opposite effect from the noise. I think, I forget the reference exactly, but in some of the literature is referred to this as anti-noise, that allows us to cancel the effect of the hardware noise rather than amplify it on average. Now, this does, while both methods are expected to have exponential scaling in terms of the sampling cost, the number of times you need to run the experiment to get good precision, empirically, zero noise extrapolation seems to be cheaper, at least versus conventional implementations or standard implementations of PEC.
Awesome, thank you. And maybe since we're at the halfway mark, we'll take one or two more questions real quick before letting Youngseok get to all of the fun results. So stay tuned. Maybe quick question here from Shi Xian. I hope I'm saying that right. You know, the results are really nice. I'm particularly impressed by the great use of error mitigation at this large scale. At the scale of hundreds of qubits, you know, Cold Atom community has also done some work with some good results and expectation values. Are those also, would you call those utility scale as well?
I guess I would. I don't want to say anything wrong, so I might have to look at the specific reference to say something with confidence. My impression is that there have been things with sort of more specialized quantum simulators as opposed to universal quantum computers, looking at simulating quantum systems at these scales. So that's one distinction I might draw with this work. But certainly, yeah, I don't know. I know there's a lot of great work going on in the Cold Atom community.
Okay. Thank you, Andrew. And Shi, feel free to elaborate. I know you got a lot of questions. Not sure we can get to all of them right now. We'll save some for the end of the talk, so stay tuned. Maybe one more from Arthur Strauss. is the method for error mitigation here coupled to the context aware calibration to enable better capturing of parameter drift that occurs over time when you have to take many, many shots? So I think it's basically a question about the drift in the systems.
Yeah, I know Youngseok did some really nice work on that. I don't know if he wants to show slides later getting into that or not. But yes, parameter drift is definitely a real thing. And so we found it necessary to periodically recalibrate and relearn the noise model during the experiment on the order of hours. So.
Good. Maybe Youngseok, you'll get to that in the second half of the talk. So I take it maybe we stay tuned for that. And then maybe a final question before we hand it back over to you, Youngseok, to tell us more about that from Diego Emilio. I think this, so basically, can you clarify the difference between utility and advantage? You mentioned this work is not a claim of advantage. What's the difference?
I think we're trying to, with utility, we were trying to draw a distinction. We're trying to suggest a break with the conventional wisdom that we would need to wait for fault tolerance to realize useful results from a quantum computer. That was the main thing. And we think that applying the fact that we can apply a error mitigation successfully at circuit volumes beyond where you're guaranteed an exact result from brute force classical methods is encouraging in that direction. I hope that's somewhat clarifying, at least.
Yeah, thank you, Andrew. And Diego, feel free to elaborate in the comments and discussion here. And folks, feel free to post your opinion as well. You can mention. By the way, Diego says, "Great, thank you for the answer." So great to see the lively discussion. I know there's maybe 4 or 5 more questions, and I can't get to all of them right now. So folks, I apologize, but we'll bring them back up at the end of the talk. And maybe in the interest of time, Youngseok, the stage is yours.
All right. Yeah. Thank you, Andrew. Zlatko. I'm going to talk about remaining part of the talk, mainly talking about what we did experimentally. So for that, I'd like to talk about what we did as an experiment. Basically, we take this transverse field easing model Hamiltonian. It's describing the spin dynamics. So we have a nearest neighbor interaction term J, a transverse field term H, and we map our spins to exactly the hardware topology, as you can see here. We take a look at the time dynamics of this system. So we trottleize first order of this Hamiltonian to get a trottleized time evolution Hamiltonian. So here we can now decompose our Hamiltonian into 2 parts, RZZ gate and then RX gate. So basically our circuit looks like single qubit gate application followed by a series of 2 qubit gates. And since we have 3-way connections in maximum in our topology, we have these collection of 2 qubit 3 layers. And we go ahead and learn all these 3 layers, and we perform our experiment accordingly. And if we repeat this structure circuit twice, that represents second Trotter step. 3 times, that represents Trotter step 3. Okay, so and one more thing here, since our experiment is more like verification and capability perspective, we are interested in comparing against the ideal solution of this trotterized circuit, not the ideal solution. So we are ignoring trotterization error here. And so when it comes to really realizing this circuit in our hardware, we need to decompose this RZZ gate into our native gates, which is CNOT. And in general, we can decompose this RZZ gate into 2 CNOTs. But at specific angle, such as -π/2 here, it can be decomposed into 1 CNOT. So you can drastically reduce the length of the circuit, earn more coherence time budget. So, but meanwhile, we still can explore other circuit parameter because we have one more parameter H. So now we are varying this parameter H or single qubit gate rotation theta H to explore different circuit parameters.
Youngseok,
Yeah.
should I worry about the Trotter error for delta t of that would give you this angle?
Yeah. So yeah, that's what I mean by here. We just first order trotterize, so there will be some trotterization error. But again, rather than looking at some interesting physical phenomena such as phase transition or something, here we are really focusing on verification purpose. So we are ignoring the trotterization error at this moment, and we are just comparing against this trotterized circuit with our experimental results.
Okay, thank you.
So yeah, one of the circuit, if we take a look that we ran, it's a 127 qubit 60 entangling layer. And if we compare that against one of the early experiment done by IBM, 4-qubit 2 depths 2 at 2017, you see quite a lot of improvement here. So this kind of illustrate how fast this field is evolving, which is pretty interesting. So yeah, coming to this diagram. So I earlier mentioned that we can explore different circuit parameter by varying parameter h or single qubit rotation theta h. And by varying that parameter, we can visit different circuit range regime. We can make our circuit Clifford, meaning we can efficiently simulate our results, even though it's 127 qubit scale. So that's a very nice verification point. And outside this circuit parameter, of course, it's a non-Clifford circuit, so it's a little bit challenging. It's challenging to obtain exact solution there. But if our qubit size is for about 30 to 40, it's still in brute force simulable regime, so that we can still get exact solution in that case, if we have reduced size. So with that in mind, let's first check the Clifford circuit to build our confidence. What I mean by that is we fix the single qubit rotation angle as a 0, and that makes our circuit Clifford. And we go ahead and learn this layer 1 to 3 collection of CNOTs. And here is the results. Y-axis is average magnetization over 127 qubit device. X-axis is Trotter step. So we go Trotter step up to 20, which is equivalent to 60 CNOT depths. And you can see the immediate signals are gradually decaying, deviating from ideal value of 1. And after we apply the mitigation scheme, it shows improved results. So you can see it's not exactly hitting 1. There might be various kinds of reasons for that, such as some model drift that that Andrew just mentioned, or some inaccuracy in our model. There might be some possibilities, but we do see a better improvement and reliable estimation on the observable we are interested in. So with that, we're moving on from Clifford circuit, and we want to try out non-Clifford circuit. So for that, we fixed the depths to 15 entangling layer, and we now vary the single qubit rotation angle theta h. So this is basically the same plot. Y-axis is the same average magnetization. But now x-axis is Rx angle, so we are varying the circuit parameter. And we know that at 0 and pi over 2 is Clifford circuit. So we know exactly what it's supposed to be, which is 1 and 0 here. And in between, it's smoothly connecting these two limits, but we don't have exact answer. So we don't know whether our answer is correct or wrong. So again, it's a non-Clifford circuit. It's not Clifford circuit beyond this 0 and pi over 2. So it's challenging to get exact solution. So that's why we approach to our collaborator Berkeley group, Professor Michael Zlatko's group, and Sajant, and ask about question whether they can verify our circuit. So this type of problem in classical approximation community, tensor network method has been one of the favorite methods to tackle this type of problem. So tensor network method is to express is a way to approximate your target wave function with physical indices. Here, it can be approximated to various type of tensor network method, such as MPS and PEPS, and different structures of these tensor network method supposed to capture different structures of the entanglement present in your system. And among them, MPS and PEPS is one of the most famous popular method. And so they choose MPS and ISO-TNS, which is a variant of PEPS. And one more important parameter to mention here is bond dimension. So bond dimension is a quantitative measure of how much entanglement we can express with your tensor network method. For instance, with this MPS method, we can think about two extremes. When bond dimension equals to 1, it's product states. We don't really capture any entanglement present in the system. The other extreme is exponentially large bond dimension, where we can exactly capture all the possibilities. But in reality, we take the bond dimension somewhere in between. Depends on the memory requirement or computational speed requirement, so on and so forth. So the Berkeley group go ahead and using MPS and ISO-TNS with certain bond dimension, they start to produce results, and we compare against each other. So here, by varying the single qubit rotation angle from 0 to pi/2, we are systematically introducing more and more entanglement present in our system. So when there's a last entanglement present in our system, they all agree in a reasonable degree, two different methods as well as experimental results. But at a certain point, you can see as we introduce more and more entanglement in our system, they start to deviate to each other. Experimental results and numerical approximation, they deviate each other. Also, among two different numerical approximation methods, they also deviate to each other. So at this moment, we don't have the exact solution, so we don't exactly know which one is right or wrong. But during our discussion, Andrew and Sajan, they realized that there's a concept of glycon. So basically, as we apply entangling gate to nearest neighbor qubit, the entanglement propagate so much that only those qubits within this glycon really matters for this particular local observable. So in our case, it's for about, the circuit is relatively shallow. So it's for about like 1 qubit or less. So that's a range, the region where we can tackle with brute force simulation. Yeah, so Sajan, go ahead and calculate the exact solution using brute force method using this glycon reduction technique. And here's the exact simulation results. And you can see there's a nice agreement between experiment results with these exact simulation results. And it seems like near pi/4 or pi/2, these regimes are really some regime that we are interested in, perhaps, and seems to be important. But it is not super clear by looking at pi/2 points whether experiment is really producing 0 or it's just depolarized and being 0. So we deliberately choose another weight 10 observable, which is supposed to produce 1 at pi/2 point. And there we still can get the exact solution using glycon reduction technique. And we saw a very similar trend here. So experiment more or less shows some agreement with exact solution, whereas pure MPS and ISO-TNS method start to deviate at a certain point. And here's another point. We utilize the learned noise model, and we performed Clifford simulation. And there we checked that the Clifford simulation results are producing pretty close to what experiment produced actually for a mitigated signal within the experimental uncertainty. This is kind of like another check whether our assumed noise model that Andrew mentioned earlier is reasonably representative. So this can be also, in other words, can be used as some sort of tool to check whether, oh, you have this circuit, you know the noise model, whether this circuit is reasonable or feasible for current hardware or not by just running this simulation. Okay, so with this check, we go a little bit further. This is weight 17 observable, which eventually includes more qubits within the glycon. And we cannot really simulate this example with brute force manner even with this glycon reduction technique. So Sajant go ahead and actually were able to simulate, still simulate and obtain exact solution using using glycon reduction MPS method. So there we still saw a very similar trend here, very consistent with the other earlier two examples. Yeah, so these are all some results that we want to share. So basically, from this observation, we kind of learned that noisy quantum computer is still able to produce the accurate expectation value at a scale beyond brute force computation. And this serves as we think this serves as evidence for the utility of quantum computing before fault tolerance. Okay. So yeah, of course, we can push a little bit further now that we know that it's producing reasonable results. We can push a little bit further beyond exact verifiable circuit, meaning we don't really have exact solution anymore for these two circuits. So basically, what we did in the left-hand side is that we effectively evolved one more further step, and we eventually don't have accessibility for exact solution anymore. But there, pi over 2, we know it's a Clifford circuit, and we know it's supposed to be 1, where we see the experimental value is close to 1. Whereas the approximation values are largely deviated from 1. And another example is in right-hand side is that we take a look local observable, but this time we go all the way to depth 60. There, the likely eventually includes all 127 qubits. Again, we saw a very similar trend where they agree each other very well at the very beginning, and they start to shows these kinds of like discrepancies between methods. So at this moment, since we don't have exact solution, we are not so sure whether this fast decay is related with, oh, maybe we go to the deeper depths, we have all these noise sources, and it's maybe because of the noise. We don't know whether it's the right answer or not anymore, right? But fortunately, after we put out these results, there are a lot of like very active discussion in the classical community. And they end up proposing various different types of numerical approximation method, some variant of the tensor network methods. And they show a very interesting trend here. These are like 6 different numerical approximation method. You can see it's the same circuit, the same example. For instance, one can maybe just naively ask, well, you have a pure MPS simulation results with certain bond dimension. Why didn't you apply similar type of extrapolation technique? So that's done by our collaborator from Berkeley, which is this purple curve. So there are like more various kinds of tensor network method proposed, and the trend is that they all agree very much when less entanglement present in the system near the 0 angle. But as we increase the entanglement present in our system and we make the circuit non-Clifford, for instance, around pi over 4 points, various methods kind of mutually start to disagree to each other at 20% level. And if we overlay our experimental results on top, some of the methods shows some sort of agreement within experimental uncertainty. So this is pretty interesting. So we are hoping that we improve our experiments so that we can provide more clarity regarding this. Also, I believe the classical community can also improve and provide more clarity on that by, for instance, spending more computational resources and increase bond dimension, so on and so forth. So this back and forth interaction is actually something we were expecting, and we think this is really beneficial to each other. In the absence of exact solution, one can perhaps use other method to check each other. If we are aware of what is assumption and approximation behind each other's method, this could be really fruitful discussion. And this continued back and forth discussion will eventually inform what kinds of circuits put classical method really challenging, And this is exactly why we are interacting with external partners for 100 by 100 challenge to identify challenging problems in various different fields. Okay, so in terms of experimental side, improving experiments, there is some optimism. So left-hand side is T1 plot. So Eagle revision 1 and revision 2 that Andrew briefly shared in earlier presentation. There has been some improvement up to 4 milliseconds in some research device. So there's some hope. Also, this is 2-qubit gate plot. There has been some improvement, as Andrew mentioned earlier as well. But there's a slightly different 2-qubit gate architecture that shows order of magnitude improvement in terms of 2-qubit gate fidelity. So yeah, there is some optimism regarding future improvement. So okay, so this is a take-home message. Last slide. We observed that a noisy quantum computer is able to produce accurate expectation value at a scale of beyond brute force classical computation. This serves as evidence for utility of quantum computing before fault-tolerant. And we kind of expected this active back and forth, and we has been observing between classical and quantum community. We are hoping that quantum experiments will motivate advances in classical simulation algorithm community and vice versa. And we view this as some sort of tool for testing near-term quantum algorithm, and we hope that this will help and encourage to explore quantum applications at non-trivial scale in near term. And since we build this trust in our device and mitigation method, we can now start to think about carefully how to choose harder circuit, for instance. And more powerful error mitigation methods are in oven, and as Andrew mentioned earlier, we put out this 100 by 100 challenge. And impending improvement is in progress, scale, quality, speed. We hope that this will further increase our access to circuit volume that we can tackle with quantum device in somewhat continuous fashion. So yeah, this is end of the presentation. Thanks for your attention and presence. I appreciate it. Thank you.
Thank you so much, Andrew and Youngseok, for this great back-to-back or two-part presentation. I think it's a really treat. It's really awesome to have that. Also, thank you, Abhinav Kandala, for answering questions here in the chat from people. There was one question which maybe is good to just bring to everybody's attention. Abhinav, thank you for giving it a quick answer, but it's what do you mean by brute force? I think Abhinav said, basically matrix multiplication, but I know that question has come up before, so feel free to add if you want, or we can jump to the next one. And folks, great time to post your questions or repost them in the Slack channel, and I'll bring them up to Andrew and Youngseok.
Yeah, I think brute force means typically this type of numerical approximation method truncate certain degree, but brute force is really just matrix multiplication type of calculation that try to capture everything, which is exponentially expensive as you scale your problem size.
Okay, great. And I guess you don't mean sparse matrix multiplication. Quick question from, maybe quick question. A question from Miguel. In the tractable cases you mentioned, or maybe just more generically in the cases you mentioned, how do the simulations compare of the classical and quantum computers when it comes to runtime or cost or memory use? In other words, accuracy is one objective and one metric, but there are things like cost or runtime, etc. Can you tell us more about the comparison there?
Yeah. So we actually had some discussion related with that in our paper. For instance, we take, this particular experiment and take a look how much time we spend to produce each individual points in quantum and classical computer resources. It's for about take like 3 hours to produce this point. 3 hours is excluding the learning time, so it might be a little bit longer than that, but more or less 3 hours or so, 4 hours or so. And these points in classical resource side produces this point takes like 9 hours or so. So it's not like drastically different they are comparable, I would say. But I think at least we know what's going on in the quantum side. So if I mention a little bit more about quantum side, there are many rooms for improvement. The actual quantum machine running time is much shorter. There are a lot of processing time in classical resources, such as like generating pulses, loading the pulses to the instrument, so on and so forth. So I would say there's large room for improvement in quantum side.
Okay, thank you, Youngseok. And thank you guys for posting questions. Please repost them or bring them up. This is a great time to post your questions. I see a few already queued up here. Maybe a quick question from Jaimyong Kim. I hope I'm pronouncing that well. I apologize if I'm not. How did you choose the expectation values you're quoting? Why those? Why not some other ones? What about higher weights, etc.?
Right, that's a really good question. First, I think we are kind of like physically motivated to look at magnetization. That's something you can like immediately think of, and the average magnetization is therefore a good representative value to describe this system, right? Rather than just like listing every individual things. And another motivation to look at this high weight observable is that it's actually a stabilizer. Where this particular Clifford circuit produces either 1 or -1. So this is the lowest weight stabilizer. So basically, this weight 10 observable is supposed to produce 1. And this is another stabilizer, which is a little bit higher weight than weight 10. This is weight 17 observable, which also supposed to produce the value of 1 at pi/2. And this is really like different choice of observable. Weight 1 here, like stabilizer here, weight 10 observable here, is that we want to explore like different circuit regimes and check. For instance, it's supposed to produce 1 in 0. That's different circuit range. Pi/2, as I mentioned earlier, there's some suspicious that, well, it can be completely depolarized. Experimental value might not be valid, right? So that's why we take a look at this another observable whose value is supposed to be 1 at pi/2.
Excellent, thank you. Maybe a question from Sinivasan. Why could you not apply probabilistic error cancellation, PEC, to these calculations?
Yeah, Andrew, do you want to answer?
Sure. So at least with the most straightforward application of probabilistic error cancellation, where you cancel every error in the circuit at every layer in the circuit, so on every qubit and on every layer in the circuit, that you can estimate what the sampling cost is without running the circuit by looking at the properties of your noise model, the error rates in your noise model, and essentially multiplying the cost of canceling every gate in the circuit. And so this grows exponentially with the circuit volume. And for these circuits, the cost that you get with that implementation is sort of like astronomical. It's measured in the time to run the experiment is measured as a large factor times the age of the universe. Now you could have, that was part of what motivated us to move towards zero noise extrapolation. There may be room for improving on that by taking into account these light cones when implementing PEC. So that's discussed, and for example, in a paper, it may still be on the archive. I don't know if it's been published yet, by Min Tran and collaborators recently, looking at how you can, if you only cancel the noise within the sort of causal light cone of the observable, you can cut down the cost of implementing it significantly. I'm not sure exactly what the cost comes to here. I think it's still going to be more expensive, but I don't have the number offhand.
Good, thank you, Andrew. And yeah, folks, there's a link in the channel to a Qiskit seminar talk on that bound in PEC if you're interested to see how that scales. Good. Question from Ruihao Lee. Great talk. Could you maybe comment on the prospect of this kind of experiments for spin models beyond the Ising model, like the Heisenberg model?
I'm not a total expert in spin models, but I think that there should be some flexibility in updating the Hamiltonians used to define the Trotter steps. So I think it could be an interesting future direction.
Yeah, I think maybe the I can add a quick comment there. It's a question of depth. They're just more expensive in depth, basically. Great. Okay, a question from VTR. How does, well, let's not post it up because it's a little funky the way it's phrased, but how does the scale is the basic question. How does the scale to larger and larger circuits? I think that might be the basic question here that is being asked.
Yeah, it's going to have an exponential cost. I think that the name of the game in near-term quantum computing is the exponential cost affordable enough to run a circuit that is interesting and useful. And hopefully as hardware error rates continue to come down and our understanding of error mitigation improves, perhaps, that will get us into the regime where we can start getting some value out of the machines.
Okay, thank you, Andrew. Quick question from Nam. I don't know why I keep saying quick question on every question. Question from Nam. Thank you very much. I see lots of collaboration, which is awesome. Great job, by the way, guys. I'm wondering, how long did it take to finish this project?
Oh, I see. I would say like on a year time frame, but it really depends on which snapshot you are looking at. I mean, this project has been continued ever since we try out. I mean, we means IBM try out 2017 like observable and try to apply zero noise extrapolation in 2019, and we try to scale that in 2021, and now we try to really scale in a, we call it utility scale in 2023. So the project itself has been really like there to continue the research. But I guess this particular paper and collaboration is like within a year time frame, I guess.
Okay, thank you, Youngseok. I think this was a question from Shi from earlier in the comments. One can also imagine performing error mitigation extrapolation classically, e.g. by performing a series of simulations with increasing bond dimension and trying to extrapolate from those. Can you tell us more about that kind of line of thinking?
Yeah, I think that's what exactly our collaborator from UC Berkeley did here. They take a pure MPS method. So they try really similar approach, extrapolating out of different bond dimension. So different bond dimension. So basically MPS is controlled approximation, meaning as you increase the bond dimension to infinite degree, it will be accurate. So the underlying reason behind of extrapolation is that this bond dimension in infinite limit will produce some accurate results, hopefully. So I think Berkeley group tried two different way of extrapolating it, like x-axis become 1 over this bond dimension, or they also tried out fidelity as an x-axis, and that's the result of this purple curve you can see here. There is some instabilities observed near pi over 2, but you know, this can be considered as one of the possible or potential technique to tackle this type of problem. But yeah.
Okay, wonderful. Maybe we'll take 1 or 2 final questions here as we're running a little bit over time. Andrew, coming back to the earlier question of scaling, could you clarify what you mean by exponential cost? Like what exponential in what, or what is the cost you're referring to?
Yeah, this might be a more involved discussion, but I'll try. In terms of the uncertainty in the exponential extrapolation, I guess, used in Z&E, if the Pauli errors within the causal light cone of the observable are generally going to cause the expectation value that we're getting out that's biased away from the true value to be causing that biased value to decay closer and closer to zero, including at the different noise amplification levels, then there'll is that exponential decay, I think, is giving you an exponential cost in your ability to resolve that point, and also to resolve the differences between the other points, such that you can meaningfully fit an exponential curve to those points and have reasonable error bars on the extrapolated result. There are also questions of whether this is separate, but there are also that's the scaling part of this. There's another question of what's the domain of validity for the exponential fit itself. I think the general form can be written as like a sum of exponentials, according to one of the papers referenced during the talk. So you may need a more complicated fit model, or you might even need to go, back to probabilistic error cancellation, so you have more of a theoretical guarantee that you're properly compensating for the errors.
Excellent, thank you, Andrew. Coming back to Arthur's question on context-aware calibration, does context-aware calibration address both spatial and temporally correlated noise, or only spatial? In other words, crosstalk occurring in the parallel gates.
So calibration, this particular calibration is done by just focusing on one layer. So I would say it's not. I would say it was not really, temporal correlation was not in mind. It's rather spatial correlation.
Okay, thank you, Youngseok. Folks, if I missed a question, I apologize dearly. Feel free to repost it. I think we'll take maybe one more. Maybe this is a big picture question from Sai. Feel free to be imaginative here. From Sai, where can quantum utility be used, this kind of quantum utility be used in the future? Who wants to take that one?
Super imaginative answer. The first thing that comes to mind is the list of possible applications of expectation values in near-term quantum algorithms, such as chemical simulations and optimization problems and machine learning kernels. I've mostly been thinking about getting the quantum computer to work these days, rather than what we will do with it once it's working. So I don't know if I have a totally satisfactory answer for that. But
okay, great. Youngseok, do you have one favorite application area you want to share?
My answer is largely the same with Andrew.
Andrew, okay. I'll share mine then. Mine is many-body quantum physics. We just put out a paper on it this Tuesday, so check that out if you're interested in materials and this kind of thing. That one's also 124 qubit thing. Okay, I think, folks, I see more questions coming in, but seeing as we are almost 10 minutes over and we've had, 30 minutes of questions probably for Andrew and Youngseok here, maybe this is a great time to thank Andrew and Youngseok for the wonderful presentation today. I saw a lot of comments from folks in the chat saying, great talk, great presentation, really clear. And I think with that, I'd also like to thank everybody who's tuned in and has been tuning in for the last 130 seminars, for making it back to the 130th. Folks, this talk will stay recorded, so you can go back and rewatch it on anything you missed. But to know what's coming up, click like and subscribe if you enjoyed it. And with that, we will see you next Friday at noon Eastern Time.